Hello, my name is Stefan De Lorenzo, and today I want to present joint work together with Martin Held that is titled An Efficient Practical Algorithm and Implementation for Computing Multiplicatively Weighted Voronoi Diagrams. I want to start with a brief problem specification. So we are given a set capital S of n input points in the plane, which we will refer to as sites, where every lowercase s in capital S is associated with a strictly positive real-valued weight W of S. An example of such a set of input sites can be seen down here, in which the site locations are highlighted in green, and the corresponding weights are just written next to their respective sites. We now want to compute the multiplicatively weighted Voronoi diagram of capital S. The multiplicatively weighted Voronoi diagram of our example point set is shown in black, and the corresponding Voronoi regions are highlighted in different colors. We all know that the standard unweighted Voronoi diagram is a widely used tool in computational geometry. An example of such an unweighted diagram can be seen down here. Its Voronoi edges are in general given by straight line segments and rays. The Voronoi regions of the unweighted Voronoi diagram stay convex in any case. Thus, the number of its vertices, edges, and faces stays linear. In other words, the unweighted Voronoi diagram has a linear combinatorial complexity in the worst case. On the other hand, we have the multiplicatively weighted Voronoi diagram. Its edges may also be formed by circular arcs. In contrast to the unweighted Voronoi diagram, the Voronoi regions of the multiplicatively weighted Voronoi diagram are possibly disconnected. And even worse than that, one can show that every Voronoi region may consist of up to linearly many connected components. Therefore, the multiplicatively weighted Voronoi diagram has a quadratic combinatorial complexity in the worst case. In our example, the Voronoi region of the site with weight 23 consists of several disconnected components. To compute the multiplicatively weighted Voronoi diagram, we propose a simple wavefront-based strategy. Our wavefront is emitted by the individual point sites and covers an increasing portion of the plane as time progresses. It consists of wavefront arcs and wavefront vertices, in which a wavefront vertex is just the common endpoint of two wavefront arcs. Whenever a wavefront arc appears or disappears, a new Voronoi node has been discovered. In our example, we see the respective wavefront at consecutive evenly distributed points in time. It is highlighted in blue. The fundamental building block of our strategy are the so-called offset circles. Every site emits exactly one offset circle that expands over time. The offset circle of a site S at time t includes all points of the plane that are in weighted distance t to S. Hence, the higher the weight of a site is, the faster its corresponding offset circle expands. Down here, we see two sites, S1 and S2, in which S1 is higher weighted than S2. The corresponding bisector, which is just the circle, is shown in black. Whenever the two offset circles initially touch, we say they trigger a collision event. From this point in time on, two moving vertices trace out the corresponding bisector. It is easy to see that the section along the offset circle of S2, which is highlighted by the dashed orange arc that lies within the offset circle of S1, will at no future point in time contribute to the wavefront again. Thus, we call such an arc inactive. Clearly, this inactive arc can be ignored from here on out. All other arcs in this constellation, even the one indicated by the solid orange line, are active, as they currently are part of the wavefront or may contribute to the wavefront at a future point in time. Thus, an active arc does not necessarily coincide with a wavefront arc. Every offset circle stores its active arcs in sorted angular order around the corresponding site in a self-balancing binary search tree. The last moment in time when they touch, we say the offset circle of S1 dominates the offset circle of S2. Thus, we will be using 3 different event types during our wavefront propagation. As I already mentioned, collision and domination events mark the initial and last contact of 2 offset circles. Additionally, an arc event takes place whenever active arcs appear or disappear. We will store these events in a priority queue ordered by the time of their occurrences. Note that the angular order of the active arcs around their respective sites only changes at events. We have prepared an animation of the wavefront-based construction of our example multiplicatively weighted Voronoi diagram. Please note that for the sake of visual clarity, we just show the active arcs. As you can see, the offset circles are admitted by the individual sites and expand at a rate that corresponds to their respective weight. Inactive arcs are successively eliminated, and the wavefront vertices trace out the Voronoi edges. If a wavefront arc appears or disappears, then we have found a new Voronoi node. We stop as soon as our event queue is empty and have constructed our multiplicatively weighted Voronoi diagram. In the naive version of our strategy, we compute all quadratically many collision events between all pairs of input sites a priori. One can now show that every moving vertex can be charged with at most constantly many arc events. Thus, in our naive approach, O of n squared arc events occur. All of these events can be handled in log n time, as they result in constantly many lookup, insert, or delete operations in a self-balancing binary search tree, or a push or pop operations in a priority queue. Thus, we get an overall runtime of n squared log n in the worst case for our naive approach. Now, experiments quickly indicate that a vast number of the collisions are invalid for general input. As the computation of all possible collisions is expensive, we want to filter out as many of them as possible in an additional preprocessing step, using a so-called overlay arrangement to improve the expected case complexity of our strategy. Note that from here on we will assume that for each site the corresponding weight is independently sampled from some probability distribution. The overlay arrangement itself is generated by incrementally constructing the unweighted Voronoi diagram of our input set S, in which the sites are inserted in the order of decreasing weight. Therefore, we first of all insert the highest weighted site S1, whose corresponding region occupies the entire plane. Whenever we insert a new site, we do not remove previously inserted edges. And we continue this process until we have inserted the lowest weighted site S10 and are finished constructing our overlay arrangement. An important concept of our theoretical considerations is the so-called candidate set of a point in the plane. In particular, the candidate set for a weighted nearest neighbor Q in R2 consists of all sites S in capital S, such that all other sites in capital S either have a smaller weight or a larger Euclidean distance to Q. Now one can show that the candidate set is fixed for all points that lie within the same face of the overlay arrangement. Furthermore, only offset circles of sites that share a common candidate set may collide. Additionally, one may prove that a candidate set consists of at most log n many sites in the expected case. The expected complexity of the overlay arrangement is bounded by n log n. Thus, we may expect to compute n log to the power 3n many collisions that may generate n log to the power 3 moving vertices. As every moving vertex may be charged with at most constantly many arc events, we also get n log to the power 3 many arc events overall in the expected case. All of these events can be handled in log n time. Hence, our strategy is able to compute the multiplicatively weighted Voronoi diagram of capital S in n log to the power 4n time in the expected case. We also developed a prototype implementation of our strategy that we used for testing. Both the computation of the overlay arrangement as well as the construction of the multiplicatively weighted Voronoi diagram are done based on exact arithmetic using the Seagull library. Our code is publicly available on GitHub and can be freely used under the GNU General Public License version 3. We tested our strategy on over 8,000 inputs ranging from 256 vertices to over 500,000. For all of these inputs, the weights were chosen uniformly at random from the interval 0 to 1. In the plot on the bottom left-hand side, you see our runtime results in microseconds for randomly chosen point locations. The other plot shows the runtime results for input in which we derive the point locations by extracting the vertices of polygons of the Salzburg database of polygonal data. In this case, the runtimes are a bit more scattered, but they do not increase. In particular, the actual geometric distribution of the sites does not have a significant impact on the runtime if the weights are chosen randomly. Therefore, our tests indicate an overall runtime of n log squared n time for these kinds of inputs. On this slide, you see the number of collision events divided through n log n, and the number of arc events divided through n, for inputs with randomly chosen weights and randomly chosen point locations. The number of arc events forms an upper bound on the number of Voronoi nodes. Random weights seem to result in general in a linear combinatorial complexity of the final multiplicatively weighted Voronoi diagram for these specific inputs. As I already mentioned, our theoretical bounds only apply for inputs whose vertices are chosen randomly. Thus, one may ask the question, how much do our experimental results depend on the randomness of our weights? To answer this question, we use the following experimental setup. We sampled our points uniformly within a square with side length square root of 2. Now let d of s be the distance of a side S in capital S from the center of the square. Furthermore, assume that R of S is a number uniformly distributed within the interval 0 to 1. We now assign the value alpha times d of s plus beta times r of s divided through alpha plus beta as weights to s, where alpha and beta are two arbitrary but fixed numbers for all of our input sides. The following plots show how the average number of candidates on the left and the total runtime on the right depend on the weights assigned to the sides. The square markers indicate the results for inputs in which the weight of each side S equals d of s. The blue triangles mark the results of inputs in which the weights have been chosen entirely at random. The other three kinds of markers indicate results where the alpha to beta ratios equal 9 to 1, 7 to 3, and 1 to 1. You can clearly see that, as one would assume, the higher the alpha value gets compared to the beta value, the bigger the candidate sets become, which also impacts the overall runtime significantly. Note that in case of non-random weights, the size of the candidate sets almost equals the input size for most of our test cases. The strategy can be easily extended to also handle weighted straight line segments. To achieve this, we need to refine our notion of a collision. Thus we distinguish between non-piercing collisions, which you can see down here, and piercing collisions. Whenever such a piercing collision event occurs, a second pair of moving vertices appears. We only need to check whether a piercing collision event happens along the wavefront. In such a case, the two new moving vertices as well as the corresponding active arc between them need to be flagged as being part of the wavefront. Now down here you see an example of a multiplicatively weighted Voronoi diagram of straight line segments, which has also been derived from one of our prototype implementations. Our basic algorithm is also able to deal with additive weights. Every offset circle that is associated with an additive weight basically just gets a head start. Additionally, our wavefront-based algorithm also implies a truly simple strategy for computing one-dimensional multiplicatively weighted Voronoi diagrams. We therefore successively eliminate the one-dimensional counterparts of our moving vertices. This yields a strategy to compute the one-dimensional multiplicatively weighted Voronoi diagram in worst-case optimal n log n time and O of n space. To sum it up, we propose a fast, practical strategy for computing multiplicatively weighted Voronoi diagrams. The expected runtime of our approach is improved by using an overlay arrangement. And we also provide a robust implementation using exact arithmetic, which is based on Seagull. With this, I'm already at the end of my presentation, and I want to thank you for your attention.